Thank you for the introduction, and thank you for being here today, although I can't see any of you, but I hope you can see me and hear me properly. So I'm excited to tell you about the kind of research we're doing in our lab, and then to take your questions in a few minutes, 27 to be exact. All right, so I'm going to start by telling you a little bit about my background, so you know why I came to be where I am today, and then maybe this kind of will prompt ideas for some of you. So I got my, I went to high school in the south of France, where I grew up. And I was always interested in STEM, so I ended up going to what is known in France as engineering schools. And so mine was called ESPCI. It's in the center of Paris. It was a lot of fun. And then when I was kind of halfway in my studies there, it's a 4-year program, they sent us to different places around the world to do what they call an industrial internship. And so I ended up working for a company for about 6 months. And this company invited a professor from Harvard to come and tour the labs. And so I had the pleasure to meet my future PhD advisor that way. And one thing leading to the other, I ended up applying to one single graduate school in the US, which was Harvard, which in retrospect was completely unusual, but it worked out. And so I ended up doing my PhD with Professor Howard Stone from Harvard University. And maybe here I'm going to place the fact that it's great to do your studies and to work with people who are fantastic scientists who can train you and give you, all the knowledge you need. But you also need these people to be kind and to be supportive, because you're going to spend their lifetime kind of turning back to them for advice and for support. So when you go ahead and choose mentors in your future, please keep that in mind. They've got to be good at what they do, but they've got to care enough about you. All right, after that, I moved on to Canada, and I did a postdoc at McGill. That was a 1-year postdoc when I started working in microfluidics and biological systems, and I helped them get started their microfluidic research in this particular lab. And then after a year, I felt that I was kind of ready to get started with my own lab. And so I took a position at Trinity College, which is a small liberal arts college in Connecticut. So a very New England type campus. The first course I taught at Trinity College had 12 students. That's how little or small the engineering program is there. It was a great place to learn how to mentor students, how to get to know your student, how to teach. But after a few years, I started really missing doing research. And so I moved to another institution. So I moved to NYU. So NYU is a university which is fairly similar to UC Santa Barbara in the sense that faculty members do teaching, but they also do quite a bit of research. And NYU is very much a scaled-down version of New York City. It's very multicultural, very fast-paced. It was a great amount of fun. But then I got offered a position here in Paradise. So I moved to UCSB in 2018, and I've been here since. One of the great pleasure of working at UCSB is first the scenery, but then also working with an amazing group of students. This is my group, and I wanted to mention in particular 2 students who are in this picture. JP Raimondi, who was an undergraduate researcher with us and who is now a graduate student at USC, and then Trin Nguyen, who is a graduate student, a researcher still in my lab. And the reason why I wanted to mention both of those students is because they are really at the heart of the project that I'm presenting today. All right, so starting in college, and that's why I had my little timeline starting back from college, I was particularly interested in fluid mechanics. And I think there is part of my interest in fluid mechanics that stem from just the beauty of fluid systems, right? If you think about the ocean, if you think about rivers, if you think about a water strider moving along a pond up there, there is a beauty into fluid mechanics, but there are also a variety of applications to fluid mechanics. You have examples here on energy and the way the wind interacts with wind turbine. You have biomedical applications, and we've all been exposed to COVID, and so there was a lot of interest in droplets and the formation of droplets back in the 2019, 2020. You can also think about a lot of industrial processes that involve fluid mechanics. So if you think about your car, for example, the paint gets on your car initially you get a primer by dipping the frame of your car into those giant baths, and then how is the liquid going to stick to the surface, right? If that's a fluid mechanics problem, and then you have those sprays, right? And so then once you apply the paint with the sprays, what should be the size of those spray? Like how densely should the droplets meet the surface of your car in order to get a uniform paint coating? So lots of application to fluid mechanics. The one that I kept oopsie daisy, let's come back. The one that I kept for the end here is the water strider, because that's really at the core of the approach that my lab is using. We're considering a lot of biological systems and trying to learn from those biological systems. And that's an approach which in engineering is called bio-inspiration or bio-inspired design. You may also have heard of it as biomimicry. And that's a pretty powerful strategy. So for example, for me now, for my research, which is on fluid flow at really small scales, you have a lot of biological examples where fluid flows have been optimized, and or have been brought to the point where they are particularly efficient, even more efficient than the engineered systems. And so we turn to those biological examples and we try and understand them so that we can design engineering processes that function better. So here are two examples here. If you think about networks of really tiny channels, the one on the left-hand side is a network of vein, right? So that's going to be thinking about the vasculature system in your body. And then on the right-hand side, you have the mycelium, which, if we want, we can consider that as the roots of the mushroom. More accurately, it's actually the organism itself, and the mushroom is the fruit. But the idea is the same, right? So if you look at the mycelium, at those structures that grow in the soil, you see that they have a structure which is fairly similar to the structure of the vasculature here on the left-hand side. You have networks of microchannels that are particularly robust, right? Because the life of these fungi depends on how efficiently you're going to be able to transport nutrients through that network of channels, through that mycelium. Same thing for us, right? If our blood stopped flowing within a section of this vasculature, then you know that the tissue would then get damaged in that region, right? So here you have two examples of biological system where flow in microchannel is very robust and works really well. If you think about the more engineered version of those microchannels, that's the example that I'm showing here at the bottom on the right-hand side, we're far from reaching this type of performance. The kind of microchannels we make in the lab to do some testing, for example, of samples, or that we use to manufacture tiny objects like particles, for example, those structures are really, really simple, and they're not particularly robust. As soon as you get a little bit of dust stuck in your microfluidic channel, everything stops, right? So we have a lot to learn from the biological systems if we want our engineered microchannels or networks of microchannel to have this robust feature that we can find in nature. So everything I'm going to talk to you about today, or a lot of the channels that I'm going to deal with today, those in which we're going to look at fluid flow, and those are going to be in the millimeter range, so about 1/8 of an inch. The reason why we're going to care about that length scale is because everything below that 1/8 of an inch is really not affected by gravity that much, right? So there are different effects there that matter, and we'll talk about those in a minute. Those are particularly common, allowing transport processes within organisms, and so I showed you two examples here at the top. Those microchannels in natural systems are very robust, 3D networks of channels growing in substrate. That's another thing that biological systems do really well. They grow, right? So you have dynamic systems or dynamic networks, which is something we don't do in engineered systems. So we have a lot that we can learn from those biological systems. And so that's kind of the whole approach that my lab is taking. We're looking at biological systems and seeing if we can get better results in terms of transport in microchannels. Okay. This approach of looking at nature to find solution is not something that we've come up with. It's actually a fairly common method. That's what I was referring to earlier as bio-inspiration or biomimicry. And you know some of them around you, right? So in the 1940s, a hiker in the Swiss Alps realized that they were getting a lot of those seeds stuck in their socks or stuck in their dog's hairs. And from there, they invented the Velcro. Right? So you imagine here on the left-hand side, sorry, I don't think I'm allowed to move that much. All right, so you imagine here on the left-hand side those seeds with spikes finishing with a hook. Well, you take that idea and you turn into one side of your Velcro strip, the other side of the Velcro strip, that's where kind of the work of the engineer comes into play. You're going to put a lot of loops in there, so those hooks have loops to connect to and to form a secure bond. One thing that I'll mention here quickly, which is a bit more of an anecdote, but Velcro was invented in the 40s. It wasn't really a huge market success right away until NASA started using it. And when NASA started using it to secure all sorts of suits that the astronauts were wearing, then it became popular enough and got traction on Earth. So sometimes you need NASA for marketing purposes. The second example here that I have of bioinspiration is more of a fluid mechanics example, where you see you have a lotus leaf here on the left-hand side, right, which is known to be water repellent. The lotus leaf wants to repel water so it doesn't get contaminated. Imagine if you have a leaf of lotus that is getting covered with water and the water is pooling there and sitting there for a while, then you're going to have bacteria that are going to start growing, and that's going to eventually damage the plant. If you're water repellent and all the water droplets can just roll off, then you keep your surface clean and without bacteria. So that's something that's particularly interesting also for engineers. And so using the knowledge they got from the structure of the lotus leaf, which is a very rough structure, but also the chemistry of the lotus leaf, which is water repellent. If you combine those two things, roughness and water repellency, then you get our modern water repellent surfaces. So this idea of you look at a biological system, you try and understand it, you try and understand how it works, optimize it by trying to model it with your knowledge of, for example, fluid mechanics in our case, and then you develop an engineered product which perform ideally even better than the biological system. Okay, so that's what my lab is doing, right? So we're trying to go from, I'm sorry about that, you're trying to go from those microfluidic 2D systems that are used to test samples, to produce droplets and particles, to analyze fluid flow, for example, in the respiratory system. We're going to get into that in a minute. And we're trying to make those systems look a lot more like a vasculature. Okay? And so the tools that we have at our disposal is we can learn from those biological systems. We have our knowledge in fluid mechanics, and we also have our knowledge in soft materials. Remember when I said, if you think about a vasculature which is growing in a body, the vessels have to form within this soft material. So you need that knowledge in soft matter. Okay, we have two approaches, two types of problems to get better at driving flow in those microchannels. The first one is we're trying to figure out if we can prevent blockages. And one system where preventing blockages is very efficient is your respiratory system, right? Your respiratory system doesn't get clogged very often, hopefully. And one of the reasons for that is because all of the particles that get inhaled are going to get stuck in mucus. And then mucus, which is a gel-type substance, meaning somewhere between liquid and solid, will actually get to move those particles away from your respiratory system, keeping your respiratory system clear and allowing you to breathe. So what if we could engineer channels that would have a sacrificial layer, like the mucus layer in your respiratory system? That's one avenue that we're exploring, and we'll talk about that in more details today. Another thing that my students are quite interested in is trying to figure out how the cilia that coat your lung and really move the mucus out of the way could be mimicked in microchannels. So could we make microchannels that are more active? And finally, that's kind of a twofold approach here on the right-hand side, which is, well, could we make networks of channels that would be more robust than the ones we do in 2D. I don't know if you noticed, but the networks of channel that I showed you for veins or for roots, those are networks that we call redundant. So if one branch of the network gets clogged or stops working, then another branch of the channel can keep working and keep feeding that region of the body or of the organism with fluid. So this type of redundancy, the type of structure of the network that we find in nature is something that we could very much learn from. How networks adapt to their surrounding, that's something that engineers don't really know how to do at this point. So that's something we would also very much like to understand and mimic. Okay? So that's kind of an overview of what kind of things that we're doing in my lab. And so today, whoops, let me come back. Today we're going to focus on the role of mucus in your respiratory system and how mucus is actually modifying the flow of fluids. And so let me tell you a bit more about your respiratory system. So your respiratory system was designed to keep or to drive air from your mouth or your trachea down into the deeper parts of your lung, right? So here what you're looking at is the trachea, right, which is in your neck. And here is a schematic of the lungs. And you see again that you have this network that keeps on branching and branching and branching, and that is particularly redundant. So the branches get smaller and smaller as you go deeper into the lungs. And the first property that I want to mention about those lungs, or this type of network, is that you have this mucus coating in most of the channels in the respiratory system. I say most of them because the ones that are deeper in your lung, the smallest channel, those don't have a mucus coating. The idea being that if there are particles or bacteria to trap, you're going to trap them in the upper part of your respiratory system, deeper into your respiratory system. It's not going to be as critical to have mucus present there. But so think about this coating of the channel, which is somewhere in between a liquid and a solid. It's a solid because it can trap particles, and once the particles are trapped, they're not going anywhere. But it's also a liquid because you have cilia, which are not really represented here. They're just represented with this dashed line. But you have cilia that are going to move the mucus toward the trachea, and eventually, you could cough, whatever was clogging your respiratory system. And the whole point of this is to make sure that anything that could cause an infection gets out of your respiratory system. Okay. If you want to think a bit more mechanically about the properties of a gel, the idea of a gel is that if you apply small forces to it, if you try and shear it at small forces, it's going to respond like a solid. It's going to deform a little bit and then bounce back. But if you apply larger forces, it's going to start flowing like a liquid. It's just going to start going and deforming indefinitely. And that's going to be what we call, and it's actually, the more you're stressing it, the thinner it's going to be, the easier it's going to be to move it. So you have what is called the yield stress fluid. Solid at low stresses, and then liquid at high stresses. That's how mucus behaves in your respiratory system. Now, the part of the respiratory system that we're all going to be particularly interested for the rest of this presentation is really the deep part of your respiratory system. So the way this works is, remember, you're bringing air or you're bringing oxygen through your trachea down into your lungs, and then you want CO2 to go from your circulatory system into your respiratory system and then out. So inhale, exhale. What happens every time you inhale is that those little raspberry-like structure, which are called alveoli, are going to expand to increase the surface of contact between the air that you've inhaled and the vessels or the circulatory system on the other side or beyond the lungs. And so for you to breathe efficiently, those alveoli need to open and close every time you're breathing in and exhaling. If those don't do their job, you're going to start getting the feeling that you're not getting enough air every time you're breathing in, right? That you're kind of drowning. And this is going to be particularly important in the rest of this presentation. We're going to try and understand how to treat people who cannot breathe properly because their alveoli don't open and close. The one bit of information that you're going to need about those alveoli is that they act like little bags, and they have a certain stiffness to it. And to reduce the stiffness of those alveoli, to make it easy for you or effortless for you to open and close your lungs, they're covered with a type of molecule that we call surfactant molecule, and that you know more commonly as soap molecule. Those soap molecules, they make it easy to create surfaces. That's the reason why you get bubbles in your bath or when you wash your dishes. Think about having soap in those alveoli, which look a little bit bubble-like, and so you would be able to open those alveoli and close them easily if you have those surfactant molecules. So there is a first category of people who is particularly sensitive to what we call acute respiratory distress syndrome, which is what I was describing as this drowning effect, right? You have a hard time getting enough oxygen into your body and then exhaling enough CO2 out of your body. This is going to be due to the fact that you're unable to open those alveoli. All those alveoli are full of fluids. That's more the grown-up version of it. In the case of premature babies, remember those surfactants that I was mentioning? If a baby is born prematurely, that means that its lungs are not fully formed. They're not fully ready to breathe in because the baby should still be, breathing through the mother. And so one of the things that a lot of premature babies encounter is acute respiratory syndrome, or distress syndrome, because they don't have those surfactants in their lung, and so they can't open their alveoli. This is what you see on the X-ray here on the right-hand side, right? You see that it looks white. It means that you're not getting enough air into the lungs. The treatment that those premature babies get, and that's where things get a little rough, is the doctors are injecting little volumes of liquid down their trachea. These plugs of liquids that are filled with drugs, which are basically those soap molecules that I was mentioning earlier, those surfactant molecules, they're going to make their way down into the lungs. And when those surfactant molecules find their way to the alveoli, then the alveoli can open quite nicely, and that's what makes their lungs look black like that. That's because they're full of air, right? And so the results are amazing. This is surfactant replacement theory was really started in the 80s in the US, and you can count in tens of thousands the number of people who were saved because they received this kind of treatment. About 1% of the kids born in the US will require this type of treatment. So it's a treatment that works really well in premature babies, but it's a treatment that does not work that well when you're dealing with adults. When you're dealing with adults that are going to end up with this type of respiratory distress for different reasons, right? Either they've been into an accident and their lungs kind of got collapsed, or they have been breathing smoke, or they've had an infection like pneumonia or COVID. Then in all of those cases, the doctors are going to want to try the same method, which is, what if we administer those drugs, those surfactants, directly into their trachea and help them breathe that way? Well, one of the things that we learned through the COVID pandemic is that it doesn't work as well in adults. And there are ideas out there. There are researchers that have done some analysis, in particular using numerical simulations that are illustrated here on the right-hand side. And they thought about two things. They thought about the fact that the respiratory systems of grown-ups is bigger than the respiratory system of infants. And so two consequences to that. The first one is adults have a lot more branching, right? So your plug of fluid with those surfactants, they have to meet a lot of intersection and still make their way all the way down to the alveoli. The second problem is when you're dealing with a bigger system, then gravity starts mattering more. So if your patient is leaning on one side, then they're going to get more of a surfactant, more of a drug on that side because gravity is pulling the fluid in. And if now they're turned in another side, then they're going to get surfactant on the other side. And so getting a nice uniform treatment of the entire respiratory system becomes tricky. Okay, so that's what was known when we started thinking about this problem. But we're fluid mechanicians, right? And we worked at the interface with soft matter, and we said, well, what happens when what's another difference between infants and grown-up? Think of a grown-up that has been suffering from pneumonia. This person has been coughing. They've been coughing a lot of mucus, right, for a while, which means that their entire respiratory system has a lot of mucus in it, which an infant does not have to start with, right? Mucus builds up over time. So we started thinking, well, how could the presence of mucus in the respiratory system affect the drug delivery? Right? And could the mucus trap some of the drugs that people are injecting into, or doctors are injecting into the trachea of patients? So here's an analogy, right? The idea, apparently this is a popular hobby in the Netherlands, so I decided to put that picture there. The idea is the mucus would be the mud, right? And your drugs that you're trying to move from point A to point B would then get lost or slow down by the presence of mud, which in our case is going to be mucus, right? And so I'm giving you the analogy with the mud, but there are also evidence, studies that have been done before we started working on this problem that showed that if you have a gel covering a surface, a gel that is easily deformed, right, that is sticky, then it's going to be hard to move fluids, to move droplets on this type of gel. And so here is your example here on the right-hand side. You see that they tried to get a water droplet to slide on one of those sticky gel, mucus-like gel. And if there is just a thin layer of that gel, the drop is moving pretty fast. In 36 minutes, it's reached the bottom. But now if you have a lot of gel, like a thick layer of mucus, then it takes 87 minutes to make it to the bottom of the slide, right? So you're slowing down. And that's kind of the two ideas what we want to test. Is could the mucus slow down the delivery of drugs, and could the mucus prevent some of the drugs from reaching deep into the respiratory system, into the alveoli? So this is our hypothesis, right? So when you come up with an idea in a research lab, you're going to formulate it as an hypothesis, right? So here is the hypothesis. The mucus lining in the respiratory system is responsible for the reduced efficiency of surfactant replacement therapy in adults as it reduces the amount of drug delivered to the alveoli. That's our hypothesis. At this point, it's an idea, right? And we need to test that idea. So different strategy to test that hypothesis, and I'm going to go quicker because I see I'm running out of time, but we had to consider how we were going to tackle this hypothesis and try and provide evidence to support or tell us that we were wrong, right? Because that happens sometimes too. So we decided to go with experimental measurements because we're an experimental group and because this would provide us with evidence. We decided to use a model experimental system so we could actually scale up all of those effects. Try and think about looking at transport in, say, the respiratory system of a mouse. Can you imagine how tiny that is? How difficult it's going to be to track every little bit of fluid? If we were able to scale that up and, say, use tubes that would be 1 inch in diameter, then things would be a lot easier not only to fabricate, but also to measure, right? So that's what we did, and that's the reason why we decided to start using bigger tubes. Now, back to something that I mentioned earlier on, remember with adults, we said when they have a bigger respiratory system, that means that they're going to be prone to the influence of gravity. We wanted to be able to increase the size of our sample so we could see things very accurately, but we didn't want gravity kind of blocking the effects that we were looking for, right? And so that's where the ISS came into play, because our experiments needed to be at such a large scale that gravity would kick in on Earth, but gravity is so much smaller on the ISS that we could run our experiments on a large scale without having to worry about gravity. So here is the experimental model. I'm going to go fairly quickly over this. We're looking at the motion of the fluid. We're looking at what's happening when the fluid, which in our case is an oil, because we need to package our sample in Santa Barbara, they need to make their way to Florida, and then they need to Kennedy Space Center, then they need to go to the ISS. If we do that with mucus, it's going to be all dried out by the time it gets to the ISS. If we do that with silicone gel, they're still going to be fine by the time they get to the ISS. So we used an oil and an oil-based gel, and we looked at the motion of fluid in the front of that volume of fluid and then in the back. So let me show you briefly. That's the setup that we came up with, and I can get back to that during the Q&A session. I'll be happy to tell you more about that. This is the timeline. We tested the system in Santa Barbara, shipped our samples with our students all the way to Kennedy Space Center. They gave the samples to NASA. NASA launched the space shuttle in November of 2023, and then we started our observations working with astronauts at the beginning of this year. And this is what it looks like on board the ISS. What you see here on the right-hand side is the microphone that the astronaut was using to tell us about what was happening. I'm going to wrap up quickly. I'm just going to take 1 minute here to tell you that when NASA tells you, tomorrow morning at 1:30 a.m., we're ready to look at your sample, you put your alarm at 1:30 a.m., you jump on a Zoom call, and you're just very excited to see the experiment happening. So that's us in the middle of the night, in Santa Barbara, kind of waiting for the experiments to happen. This is our implementation partner and their control room in Colorado. There's only one person who can talk to the astronaut, otherwise that would be chaos. And this person is Shankini here on the right-hand side. And she's talking directly to the astronaut and helping them walk their way through these fairly complicated experimental procedure. And we got to work with Butch Wilmore as of a couple of weeks ago, and that was amazing. So this is a short video. I can probably play that really quickly while I kind of conclude. This is a video of our experiment. You may remember the little sticker that was on my first slide up there. This was the first astronaut who helped us with our experiment, Laurel O'Hara. And so I can, again, tell you more about those experiments. But you see how we went from the respiratory system that was such a complicated system to one tube here, which is what is behind Laurel's arm, and looking at the flow of fluid in that tiny region. Okay, these are the results of the first experiments. I can go back to that, but I'm actually not going to be able to tell you too much about the results. I can't even tell you if we verified our hypothesis or if those results are going to tell us that our hypothesis is completely wrong, because we just got the data. So we're going to spend the summer analyzing those data. The first results we're seeing are promising, so that's the reassuring part. But I wanted to tell you about this adventure of coming up with an idea, an hypothesis on Earth, getting to work with astronauts on board the ISS, and then kind of the summer ahead of us of analyzing data and making sense of all of their hard work up in space. So I want to thank you for your attention. I realize I've gone a little over, but I would be really happy to take any question you may have. Thanks.